Hello. Disproportionate collapse is exactly what it says on the tin. It's the collapse of a building that is disproportionate to the incident that triggered the collapse. The UK's most infamous example is Ronan Point in London, where in 1968 there was a gas explosion in an 18th floor flat which blew out some load-bearing walls. This led to the collapse of the floors above, killing 4 people and injuring 17. The pressure force from this gas explosion was actually quite small, so should not have caused this extent of collapse. This incident helped shape the regulations as we know them today. We describe a building that won't collapse disproportionately as robust. When I'm checking calculations and drawings for a building, the first thing that I want to be told is the building consequence class. If this is stated, it gives me more confidence that disproportionate collapse is being considered. Building consequence classes are set out in Table 11 of Approved Document A of the Building Regulations, which is on screen now. You can also find consequence classes in Table A1 of BSEN 1991-17, Actions on Structures. Consequence Class 2B is where the structural requirements become more onerous. This class includes 5-storey or more residential buildings and retail buildings of 4 stories or more. When a structural engineer designs a building to be robust, they first decide whether to design for the risk of identifiable accidental forces or unidentifiable accidental forces. If the risk of an accidental force can be identified, then the structural engineer must design for that risk. For example, these might include car impact if the building has an underground car park, lorry impact in a loading bay, an industrial process that could cause explosion. The design engineer must either remove the risk, e.g. by relocating the industrial process, or design the structure to withstand the force associated with the risk. Whether or not there are any identifiable risks, the engineer must always design to a baseline risk level. There are 3 ways to do this. Firstly, to provide vertical and horizontal ties, to analyse what happens to the building if a load-bearing element, which might be a wall, column or beam, is removed, or to design an element as a key element or protected element that has capacity to sustain a pressure of 34 kilonewtons per square metre. With a steel or concrete building, providing vertical and horizontal ties is relatively easy because steel connections and reinforced concrete joints have inherent tie capacities. However, as checking engineers, we would like to see a calculation for the tie forces. The next approach is the removal of load-bearing elements. This approach looks at what happens to a building structure when elements are removed one at a time. The aim is that there should be little or no collapse. The amount of collapse allowed is 15% of the floor area, or 100 square metres, whichever is the smaller value. This approach is generally taken with masonry and timber buildings. Remember, it's only really buildings of Class 2B or higher for which the design engineer needs to take this approach. A normal masonry or platform timber frame house will be a Class 1 or possibly Class 2A building, and the details required for robustness are inherent in the form of construction. The final approach is designing an important bit of structure as a key element, and it's relatively straightforward. It involves ensuring that the key element in question, whether it's a wall or column or a beam carrying load-bearing elements, has capacity to resist a pressure of 34 kilonewtons per square metre. This figure was derived from the force of the gas explosion at Ronan Point. A column will present only a small area of elevation to the pressure force, and therefore it is typical to use a higher force than this figure. It is also important to note that if there are transverse structures, the horizontal and vertical ties may not be able to be continuous from roof to foundation. In this case, the design engineer will probably need to take a different approach for the transverse structure, like designing it as a key element. There are other elements of structure that are integral to a building's robustness. If a building has floors that cantilever over a smaller floor plan, and these cantilevers support multiple floors above, the integrity of the cantilever is absolutely crucial for the safety of the floors above. It will be necessary to design these cantilevers as key elements, and the same applies to other essential bits of structure. Remember, in addition to this baseline level, it's important to design for any identifiable accidental forces that may occur. So a concrete building may be designed with horizontal and vertical ties for the unknown accidental force. But if there is a basement car park, those basement columns do need to be designed for car impact loads. Alterations of existing buildings can provide a challenge for a number of reasons. Firstly, if the building is older, it may not have been designed to meet current standards for robustness and disproportionate collapse. Secondly, the proposed alterations may change the consequence class of the building. Common occurrences of this are when an additional floor is added to a building, changing it from a Class 2A building to a Class 2B building, or if the use of the building changes, which may also alter the building class. Be aware that retrospectively fitting horizontal ties and vertical ties to an existing building may be challenging. I hope this has given you an overview of some of the considerations for structural robustness and disproportionate collapse. Remember, every building is different, so always speak to your building control provider if you have any doubts. If you enjoyed this video, please give it a like and subscribe to our channels. And if you have any questions, just get in touch via the number that's on screen now. Thank you for watching.